we have here Zoltan. Zoltan is also a friend of mine because I have been. This has been a benevolent dictatorship. I have hand picked up my speakers, and Zoltan has agreed to talk to you. I believe that he's going to talk about the growth of black holes, massive black holes in general. And I hope that he will use very few slides, but he kind of promised that already. So go ahead, whenever you want, Zoltan.
Yeah, thank you. Actually, first of all, thanks. I'm very happy to attend this event, and I wish, of course, I was in person in Havana, which would be even nicer. But thanks for putting this together. I only have one slide I was trying to share, which is not very scientific, but I wanted to share. Can you actually see this if I share my screen?
Yes, yes.
Somebody should tell me. So when I looked at the website of the event you organized, first I thought you put up a picture of Columbia University in New York City, where I'm sitting right now. So you can see on your screen. I took a picture of my university this morning. It looks well, it looks clearly similar to University of Havana. The statue, even though the statue was designed by two different artists, the universities were built around the same time, and it has a very similar feel. So I felt very much at home coming to this meeting.
But you have more columns. You have a lot of them.
Sorry?
You have more columns.
Yes, we do have more columns, and I think the surroundings are probably quite different. I don't know. I've never been in Havana. Our university is in the middle of the city, so it's surrounded by lots of other buildings. So I hope to visit Havana University one day and spot the 10 differences. So I think that was my only slide potentially. I'm going to stop sharing the screen. So actually, what I wanted to talk really about two different topics which are related, and the first one is that there are very, very massive black holes, which we now know exist in the very distant universe when the universe was very young. And so I wanted to present the current picture of these black holes, how we found them, how do we know they're there, why is it surprising, and how we think they might have been born. But actually, number two topic would be the part of this growth is probably very likely involve mergers of black holes. So this ties very nicely into Qian's previous talk, because it is actually not trivial to convince two black holes to coalesce. And I think I will probably also talk about that in the second half. And actually, I really enjoyed Pau's idea of lots of interruptions, so please feel free to interrupt at any time. So I'm going to start just assuming that most audience members are not astronomers or astrophysicists, so I want to describe from very basics the situation with massive black holes. So in fact, maybe a good place to start is that we know, as Qian already mentioned in previous talk, that we know from observations that there is a massive black hole between in the nucleus of galaxies which are nearby, relatively nearby, and their masses range from about 1 million to about 1 billion, or actually 10 billion times the mass of the sun. Now, the way we tell these black holes exist I think you also had a talk about the galactic center. So I think, is that true, Pau, actually?
Yes, that's true. Yesterday with Real Sudel.
So I think you know that we know very well that there is a massive black hole in the center of the Milky Way. Because
we have a supermassive dark object.
Yes, a very heavy object, which is about 1 million times heavier than the Sun, and it's condensed into a region which is roughly 100 times its own Schwarzschild radius if it was really a black hole. So it's and the reason we know this is because we follow the motions of individual stars, and because v squared over r equals the acceleration is gm over r squared. If they go very fast, if you measure very rapid velocities, v is large, then you can measure that m is very large. I mean, very roughly speaking. And this can only be done, unfortunately, in our own galaxy, because I don't know if it was emphasized in that talk, but in order to resolve these stars, the angular resolution has to be something like, you would have to be able to resolve me from Havana. It's a milliarc second resolution on the sky. So the angular resolution is equivalent to the angle I would subtend if you look at me from Cuba. It's extremely difficult. It's possible in the galactic center, but it's not possible in other galaxies. But nevertheless, in other galaxies, it is possible to look at the nuclear regions and observe and collect the light from the nucleus, and you don't see individual stars resolved. They just appear in one pixel in the spectrograph, but you still see very broad lines indicating there are very large velocities. So you could still infer the presence of massive black holes. And this works for about over 100 nearby galaxies. So these galaxies are, of course, very mature, and we're pretty sure they have these very massive black holes in their centers. And every time we look and are able to tell, there is a black hole. And so that's interesting. Now these black holes are very massive. So maybe it's worth just saying that we also don't know where exactly these massive black holes came from. But it's even more interesting to look backward in even more distant universe and discuss this finding, which is about 20 years old finding, that these kind of black holes exist very early on. So just to appreciate that, I want to say a few more very basic things. So first of all, I think you probably know this, but black holes, of course, are generally thought to be very dark because light cannot escape from inside their event horizon. But they're actually extremely bright when you throw matter into them. So if a black hole is sitting in the middle of a galaxy, and there's not much gas around, just an old galaxy with no more gas left, out of which stars had previously formed, just some stars orbiting the black hole, then not much is happening, and it's very dim. But most galaxies do have some gas in their nuclei, and about 1% of galaxies have sufficient amount of gas that it's falling continuously into a black hole in the nucleus, and is fueling something called an accretion disk, which, because it reaches so near the horizon, it accelerates to near the speed of light. So this gas that's swirling around the black hole is traveling nearly at the speed of light, and has internal friction. So it heats up to very large temperature and liberating lots of energy. The details of that process are also interesting, but I wasn't going to discuss that physics. I was just going to make the point that these massive black holes can be extremely bright. They're called quasars when they are bright. and they basically outshine the whole galaxy in that case. In fact, the reason they're called quasars is because they outshine their host galaxy. They're brighter than the entire galaxy, and therefore they appear as point sources on the sky. At least they did until the Hubble Space Telescope came around. And so they thought first in the 1960s that these were stars on the sky. And so quasi-stellar sources is where the name comes from. So this later, of course, was realized that when you are able to take a spectra of these objects, that they're very distant. And the reason this is important for my story is that because they're so bright, they can be seen out to a very large distance. So quasars can be seen essentially as far away as we see anything in our universe at this moment, meaning other galaxies. So to appreciate exactly how far we have seen quasars, I think I should say something else, which is slightly different, which is that we live in a special time because we understand roughly speaking. I think you also have talks about this at this meeting. Well, we understand the universe is 13.7 billion years old and had a beginning. And in the beginning, there were no stars and galaxies. It was very small, and there were fluctuations imprinted in the early universe when it was expanding very rapidly. And we understand that these small fluctuations got amplified as the background universe overall was expanding. The contrast between overdense regions and their surroundings grew over time. And this can be described mathematically, but I didn't bring slides, but it's a very intuitive process. If you imagine the universe is a baby, it's tiny, it's very dense, but there's some particular spot which is denser than its surroundings, then there'll be some net acceleration towards the center of mass of that overdense region. And because the force is pulling the nearby material towards the center of mass of the overdense region, it's going to expand a little less rapidly than the average universe is expanding, which makes this region even more overdense. And when it's even more overdense, it's going to be even more exerting additional force on its surroundings. So it will be even more decelerating, and then this is called the gravitational instability. And this leads eventually to regions separating from the expanding universe and collapsing on themselves. And the interesting point about this is that this is very well understood and very well quantifiable, reasonable, simple fashion, based on just equations of how perturbations grow and how large the amplitudes there were in the beginning, which we also know empirically.
Wait, Sultan, I'm not sure. Is everybody following? Because I see that nobody's asking questions.
Yeah, that's good.
Yes, as a trick, Xian was actually asking questions before to the students. And that turned out to work out quite well. Jose, I don't know, Diana, people, I want you to interrupt Sultan.
Yeah.
Is everything clear? I don't think so. Boris. Don't be shy.
Hi. I'm not asking question, but I'm still processing your ideas also.
Which means that, yes.
Yeah. So yeah, you can ask me. I mean, I think we would be happy if you ask me. So for example, I'm slowly building up a case that we have seen these very distant, very bright black holes. But does it surprise people that that black holes can be so bright, or does that make sense to people? Because usually
Yes.
when I first mention this, people tend to be surprised that black holes are so bright. So we could. Well, does that make sense to people or not?
Yes, Jose, for instance, our Milky Way, is it a quasar or what is it? Is it bright? Is it what is it? What do you think? Do you understand what is a quasar?
I'm not sure I'm following correctly. Could you repeat the idea of a quasar? And you say that a black hole is bright, but in what sense of bright?
So when so very good. So I'm glad, Pau, you stopped me. So let's go back to the idea that there is a massive black hole in the center of our galaxy, right? So this I think has been discussed, but that black hole, we don't actually see that black hole. If you look on the sky, you don't see a bright spot on the sky where the center of our galaxy is. It's in fact completely dark. There's nothing there to see. The only reason we know this massive object is there is indirectly inferring its presence from the motions of the stars around it. Right? Does that make sense? So when
yes, we saw that yesterday, right? Do you remember these people?
Yes, I imagine it can be similar to the presence of dark matter or something. It's inferred because of the movement of the things on its influence.
Yeah, it's a very good analogy. So in fact, you could call it dark matter because we infer its presence from its gravitational pull on surrounding objects, but it's not emitting any light. But what do people expect to see on the sky? If you look at a nearby galaxy, I mean, you've seen images of galaxies, right? A typical galaxy looks like the Milky Way, which it's got a spiral. It's got a disk, for example. If it's a disk galaxy and has lots of stars extending on the sky, and what do you expect to see if there's a central black hole? I mean, I like the idea of asking you this question. What do you expect to see on the sky if you have another galaxy with a black hole in the center, similar to ours?
Rainer?
Well, truly, I don't know.
I guess, maybe. I guess.
You're allowed to guess. It's not a trick question.
I mean,
Well,
Go ahead, people, talk.
technically we should see nothing, right?
Yeah, so exactly. So if it's like our galaxy, and you look at the black hole in the middle, which is sitting there, in fact you don't see anything at all. In fact, even more generally, if there's a black hole somewhere nearby in the universe and you're looking at it, you just don't see anything. It's just a nothing. The black hole itself is just a point in space-time, but you don't actually see anything. It's a nothingness. Now,
sorry,
let's
can I ask about that?
Sure.
Why would we see nothing? Why would we not see light from behind that object lensed around it?
Yeah, very good. So now you're saying there's something else, not just the black hole, but there's some light source. So now you're talking about some source of light that's behind the black hole, right?
Yeah.
So that's not the black hole. If there is another source of light, then you're correct. The black hole can have an effect by changing the direction of the rays of light and causing gravitational lensing. So you can see the presence of the black hole this way. Actually, you can.
But if we look at the center of the Milky Way, do we see nothing, or do we see some light, which
So
we
when
could
you-
attribute to being behind it and lensed?
So the answer is that actually we don't see anything lensed because in order to see the lensing, you have to be extremely precisely aligned. Your light bulb you're imagining behind the black hole would have to be aligned with the black hole as the lens, so that us and the black hole and the light source behind it is on a straight line. And the probability of that happening, so there are stars going around behind the black hole, but the probability of such an alignment is just too small. It just doesn't happen.
Yeah, makes sense. Yeah.
Now, it's possible that there is some plasma which is circling around the black hole in addition to the stars. And generally, if you have plasma and it's being pulled by the black hole, it tends to be accelerating towards the black hole. So now maybe again I should phrase this as a question. So what do you expect to see if the black hole is not sitting in vacuum, or vacuum plus some stars going around it, but is sitting in the center of a galaxy where there is some material in the form of ionized plasma which has fallen to the nucleus from further outside regions of the galaxy? Then what would you expect to see?
Could it form a disk?
Exactly, that's a good point. So first of all, in general, if you have a gravitating point mass and stuff is falling towards it, unless you're in a physics class at the university, or if you're solving a homework problem, nothing is perfectly spherically symmetric. So the infalling of the gas will have some net angular momentum, and if there's some net angular momentum, then when the gas condenses, it will form a disk with a direction determined by the net angular momentum. Now, the key point, which I think maybe is harder to appreciate, but this disk, if there's enough plasma, is going to be very bright. And does anybody have any guess why it's so bright?
Is this because it's highly accelerated ions?
Yes. So what is the source of energy? So for example, a star shines. What is the source of energy?
The nucleosynthesis.
Exactly. So you're getting energy by transforming nuclei, let's say from hydrogen to helium. That's your energy source. And ultimately, it comes out as photons from the star. Now, what is the energy source? If you're throwing some plasma, it's forming a disk, falling into the black hole. What is the energy source? Any guess?
Jose.
Gravity itself?
Yeah, exactly. So essentially you're using the you're using the in this disk the gravitational potential energy as the mass is moving inward, and because the radius of the black hole is so small compared to anything else, the potential energy is Gm over R, and R is really small. So you're extracting a lot of energy.
Okay, so this is perhaps a stupid question, but isn't the gravitational force conservative? And so how would we be, I suppose, injecting energy into the system?
So no, that's not a stupid question. So that's a very good question. So now we'll have to actually go into some topics which are not fully understood. But if you just put some stuff around the black hole and just let it go in a conservative fashion, it's just going to go on a circular or elliptical orbit, and is not going to move towards the black hole and fall into the black hole. The reason we believe that it does is that if you think of a Keplerian accretion disk, meaning, so let's simplify our description. There's a black hole in the middle. There's a circular ring of gas just going on a circular orbit. But then outside it is another ring of gas, an adjacent annulus, which is also going around. And the speed, the tangential speed, if you just think, if you're far from the black hole, it's a completely Newtonian disk, meaning the velocity, the orbital velocity. I hope people, so how does the velocity then depend on radius?
Cuba people, come on, this is for you.
Yeah, this is not a trick question.
Come on, Jose, I'm looking at you. He's hiding. Rainer, Diana.
So this is not a trick question. It's just Gm over R. Gm over R squared is the force, is equal to V squared over R, the acceleration. So V squared goes like 1 over R. So V goes like 1 over square root of R. That means the outer ring goes slower and the inner ring goes faster. And that means in between these two rings, there's some internal friction. Now, does that make sense to people? So we have two rings. It's like the moon going around the sun. It takes 1 year. But if you look at the planets further out, they take longer than 1 year because they're farther away. So by analogy, if you have a ring of gas going around the black hole and another ring of gas further out, you have some internal friction because these two rings are not going at the same speed. And this friction generates heat, which then generates radiation, which then emanates as photons. So ultimately, I don't know who asked this question, isn't gravity conservative? The answer is yes, gravity itself is conservative, but there is plasma physics processes which take place due to this friction, which is not conservative. It converts orbital velocity ultimately to photons and allows gas to flow inward. Does that make sense?
Yeah, that makes sense. Thank you.
Now,
Yes.
now in fact, another thing that that illuminates, well, maybe I should actually move on. So, because I do want to get to some theoretical points, but so the point of this is that you have extremely rapidly spinning gas around the black hole with very high level of friction. So it's very, very bright. So now what do you expect to see if you look at a galaxy which has enough gas in its nucleus to light up such an accretion disk? Again, this is not a trick question, but anybody can guess. What would you see? I kind of already said it. So if you pay attention, you can cheat and tell me. What would you see on the sky? If, let's say, the Andromeda galaxy, our neighbor, was rich in gas in its nucleus, what would you see on the sky?
Bright spot, maybe?
Yeah, exactly. You would see an extremely bright spot. Now, it would be very small because the Schwarzschild radius, the inner region where this friction is very high, where gas is going near the speed of light, does anybody remember the Schwarzschild radius for the sun? That's kind of important actually for the story. So I don't know if you remember how much should we compress the sun so that it becomes a black hole?
Sean actually mentioned this before, I think. So go ahead. Anyone?
3 kilometers, maybe?
About three.
Yes.
About
Yeah.
3. Yeah.
Yeah, exactly. It's 3 kilometers. So that's the sun. Now, this number goes linearly with the mass. So for let's say a 10 to the 6 solar mass black hole that's in the center of our own galaxy, it's 3 million kilometers. Now, is 3 million kilometers a large number or a small number? So what is 3 million kilometers? Is it small or large?
Compared to the radius of typical astronomical bodies, very large. Compared to the distances between them, not that large.
Well, so let's do a comparison. So how big? Let's say let's convert to centimeters. How many? 3 million kilometers is a kilometer is 10 to the 5 centimeters. So 3 million kilometers is 3 times 10 to the 11. Let's forget the 3. So it's 10 to the 11 centimeters. So what is the distance, let's say, between the Earth and the Sun? Anybody remember that number?
It takes like about 8 minutes for the light of the sun to reach the Earth.
That's correct, yes. So it's 8 light minutes. So what is that in centimeters?
10 to the 8 centimeters per second is the speed of light. Then 8 minutes is about 480 seconds.
Roughly 10 to the 13
Right.
centimeters?
Yes.
Or 1 to the 13? 1
Yeah.
by 10 to the 13. Yeah.
Yeah, very good. So what we've concluded is the effective size of a million solar mass black hole, where the horizon is 10 to the 11 centimeters, which is 1% of the distance of the Sun and the Earth. So it's absolutely tiny. So let's say you have a disk swirling around it, which is 100 times bigger. Then it's basically the size of the solar system. Now, what is the so now we're saying there's a galaxy. There's a very bright spot in the center, emanating from a region which is size of the solar system. Now, how big is a typical galaxy, like our own galaxy? How much bigger than the solar system? So our solar system, we said, is 10 to the 13 centimeters. Anybody knows the size of our galaxy? Now we have to use centimeters. So anybody knows the size of our galaxy?
In centimeters.
About 10 to the power 22.
Yeah, that's good. So it's
10 to
about
the power 22 centimeter. Yeah.
yeah, exactly. So now we're talking about a region in the center of the galaxy that's 10 to the 13 centimeters, occupying this region in a galaxy that's 10 to the 22 centimeters. So it's a billion. It's 1 billionth of the galaxy. It's absolutely tiny. So physically, this region, which is extremely bright spot, is very, very small. So you see a bright spot on the sky. Now, of course, we have technological limitations because our telescopes don't resolve such a tiny region. So it just looks, in practice with a telescope, depending on how far this object is, it can just look like one single bright spot, and you don't even see the rest of the galaxy. So this is what I meant this is what I alluded to as a quasar. Is this concept clearer now? Well, actually, I hope it's clear.
Yes.
But what? So, but just to make sure it's clear. So, why would you not see the galaxy? If this region is, let's just stick to this number. I have a distant galaxy. I look at it with some telescope, and there is a bright, tiny point-like light bulb in the center, which is much brighter than the rest of the galaxy, but it obscures the galaxy. Why is that? Anybody can guess?
So Zoltan, what is the question? Where is this energy coming from, or why is
No,
it,
just I'm trying to impress on you that these quasars are just a point on the sky and not a galaxy with a bright spot in the middle.
oh,
So this is just a technical question.
okay.
Is it a contrast type of problem? That the contrast is we won't be able to see the faintest part of the galaxy and we only see the brightest spot.
Yeah, I think you could phrase it that way. But essentially, the telescopes have an angular resolution, something called the point spread function. So an infinitely small thing will appear finite in size because of the diffraction, let's say, or just by the atmospheric fluctuations on the Earth. So in reality, if that point is really bright, it will not allow you to see the rest of the galaxy because it becomes a smudge with the telescope.
Oh, given that is very interesting. Given that, wouldn't that fact prevent us or make it difficult for us to estimate the size, the mass of a galaxy based on its luminosity?
Yeah, so that's actually now a very good question. So that's a very good point. So these quasars, so these are, as I said, they're called quasars. And the reason they're called quasars because it's an abbreviation for quasi-stellar source. And because people initially thought they were stars. So obviously you must be correct because people didn't realize, because you just see a point source on the sky. People in the beginning, in the 1960s, when quasars were discovered, people didn't realize that they're extremely bright, very distant objects. They thought they were stars in our own galaxy because it's just a point.
And what about the method? Just before going forward, couldn't we measure the lines of the different components and compare them to stars to say that or do they look also the same?
No, so this is the point. So in the 1960s, this was a long time ago, it became possible to take spectra of these point-like sources, and the spectrum looks very different from a star. So already it was obvious from the spectral shape that it's not a star. But moreover, there are lines in the spectrum which can be identified with various elements of the periodic table, from hydrogen, helium, nitrogen, oxygen, carbon, which are emission lines, which are caused by exciting transitions between atomic levels in the plasma that's in this disk, let's say, very, very crudely speaking. So the gas that's emitting near the black hole is producing these lines, but these lines are at the wrong wavelength overall. So actually, I don't know if I need to explain redshift. Can somebody tell me if you know what redshift is? Cosmological redshift. I need to, yeah. Can somebody say, do you know cosmological redshift?
I at least am familiar. It's the lengthening of wavelengths as it travels across cosmological distances due to the expanding of space.
Yes, correct. So I don't know if do others know. Does everybody know this, or have you not learned this in class?
Just let me check on the queue of people. Jose, Joel, Auris, all of you. So Nick, can you hear us, by the way? Is this concept clear to you?
Yes, I can.
Nick. So are you fluent? Do you know what is this?
No, I don't. And
okay.
In the INSTEC, our astrophysics background is very poor, in fact. So in these topics, no, we're not so strong in our knowledge. If you know
fine.
what I mean.
Yeah,
Yeah,
no,
this is completely fine. This is the reason of this for these talks.
Exactly. So, I mean, eventually you can learn this, but there's a. So I would like to explain in 2 minutes or 1 minute that the universe is expanding, and just the setup is that this expansion obeys, Einstein's equations of general relativity, and in general relativity, I don't know. Okay, here's another question. How many have you taken general relativity, or not yet?
So now,
Yeah, some of us did.
So for those of you, this will be familiar. But is there anybody who did not take general relativity? Because I want to say one thing about general relativity that's important for this redshift.
maybe Andrew. What about the rest of you? Come on, people. Say yes, no.
I did.
Okay, so let me say one thing. And for those of you who took it, it's a reminder that if you want to follow the motion, okay, I'm sure you all know that in Newtonian theory, if you want to follow the motion of an object, then you solve the equation of motion, F equals ma. You say there's a gravitational force which causes acceleration, and you solve the equation of motion. And then you can plot the trajectory of your ball, of your particle or ball or whatever it is, in space as a function of time, by solving this equation F equals ma, where F is the gravitational force. So this I assume everybody's done. So in general relativity, there is no such thing as an equation of motion because first of all, things have trajectories through space-time, not moving in space as a function of time. There's just a trajectory in space-time, and the way there's an equation called the Geodesic Equation, which you solve in general relativity, where there's no forces. You simply solve an equation where the objects follow the curvature of space-time, not space, but space-time. So I'm sure you've seen pictures. I don't know if you have, but I assume, have you seen pictures where general relativity is demonstrated by showing it's like a rubber sheet, which instead of flat, it's curved. Have you seen these kind of pictures?
Yes.
And so then I'm sure you can imagine. You put a test particle there. The curved rubber sheet represents space-time, and then if you put a test particle, it follows the curvature, meaning it goes on the shortest distance between 2 points on this curved surface. So that's basically how you obtain motions of particles. But when you do this, our universe is expanding, so our background space-time is, roughly speaking, just a homogeneous and isotropic space-time which looks the same everywhere in the same direction, but overall it's expanding. And if you solve this geodesic equation in an expanding space-time, what you discover is that the momentum of a particle goes down, decreases with time, as 1 over the expansion of the overall scale of your universe. Meaning, there's a very simple conclusion from these equations. If there are small test particles going in some random direction of the universe, then during the time the universe expands by a factor of 2, the momentum of this particle decreases by a factor of 2. So I'm sure you didn't follow because I didn't solve equations, but can you tell me if the statement makes sense to you? Or
So
So it doesn't mean that the expansion of universe changes the curvature of space-time. So at some point, space-time feels different for this particle in whatever it is because of the expansion of universe. That's what you're saying.
So in this way of what I'm saying is that we are assuming this particle is really small. It doesn't do anything to the universe. It's a test particle. And the universe is just homogeneous, isotropic, and it's just expanding. And you're actually right, the curvature is changing. But this curvature is measured in 4 dimensions. And it's changing over time. But what's more relevant is that the particle is essentially losing its momentum. So one way to visualize it is you have an expanding balloon, and on the surface there are particles rolling around, but they're slowing down because of the expansion. So they're all trying to come to rest with respect to the rest of the universe. Now for photons, this means they lose their energy. Now photons cannot slow down. So when you lose their momentum, they cannot slow down, so they lose energy instead. And so if you look at a distant object which emitted a photon when the universe was half the current size, then that photon, by the time we detect it, will lose half of its energy. Which means if you see an emission line, which is at a particular, well, okay, let me quiz you. So you know that how energy of a photon is related to the wavelength. Do you remember how? How is the photon energy related to the wavelength?
Inversely related.
Yeah, very good. So that means you have a photon. It was produced by some excitation of some hydrogen atom when the universe was half of its present size. Then we observe it now in our detector. Of course, it's much later. Some billion years have passed. The photon has all this time was traveling on a straight line towards us and lost half of its energy. And as you said, the wavelength is inversely related, so that means the wavelength will be double. So in particular, the Lyman alpha emission line, for example, is the most prominent line of hydrogen. It's the energy, it's the wavelength that corresponds to the energy difference between the first excited state and the ground state of the hydrogen atom. That's 1,1200 angstrom, or 0.12 microns. So a quasar that you see now, which lived in the past universe when the universe was smaller, the wavelength of this line will be moved from 1215 angstrom to some larger number. So if the quasar was born when the universe was half the size, then this will be 2,430 angstroms. So this is what we call redshift, because, well, it's called redshift because the direction is the same as if you, I'm sure the more familiar example of a photon changing its wavelength is if the source is moving, which is a completely different effect. But if you take a light source and it's moving away from you at half the speed of light, then the same effect arises. The wavelength will be doubled. And that's called redshift. So, except this is a different effect. This has nothing to do with velocities, has to do with the expanding universe. And it allows us to immediately tell if you see a quasar when the light of that quasar was actually emitted. So is that clear actually so far then? Because now I can almost state the puzzle. Now it will make more sense. So what happened in the 1960s, the quasars were observed, spectra were taken, and it was realized that they're very far, but very far meaning that their emission lines were redshifted, but only by 20, 30, 40%. So that means the light left the host galaxies of those quasars. The light left those host galaxies when the universe was 30, 40% smaller than now. And that was in the 60s, 70s. And the exciting thing that I'm going to talk, I guess, for the remaining half an hour is that in the last 10, 20 years, we have seen quasars, which are very similar, point sources on the sky. But these lines are shifted by up to a factor of 8. So that means we are seeing quasars. We know they're quasars because their spectral shape and the series of lines are extremely easily identifiable, at least distinguishable from stars or galaxies. And the lines are shifted by a factor of 8. So that means these quasars actually lived when the universe was 8 times smaller than today.
Sorry, why is it 8 times smaller? Is the because I have an idea that the rate of the expansion is not constant, but if I guess I feel that to have this simple relationship, something would need to be constant, which is not.
Okay, I think not exactly sure what you're asking in terms of why is it 8, but
well, I'm saying if the wavelength is shifted by 8 times, then to say that this means the universe was exactly 8 times smaller when this light was created.
Yes, that is exactly. So you're surprised by this, I guess.
Yeah, I would imagine that since the rate of expansion is changing, it would require some integral over the expansion rate.
Okay, very good. I'm very glad you asked this. Really good question. So in fact, no. The number 8, if you see a line that's shifted by a factor of 8, which we did, it's an empirical fact. We know the universe was exactly 8 times smaller. It's a linear relation. And in fact, what you have in mind is you're trying to associate the redshift with the velocity. And you're talking about the expansion rate. Because mentally you're thinking that this stretching of the line is caused by the expansion rate or the expansion velocity. And that's very good you said this, because in fact that's not the case. This redshift has nothing to do with velocity. In fact, if you could externally, is there somebody? There's a lot of noise. Can you hear me?
Actually, yeah, I can hear you, and okay. I think I just realized why the velocity does not matter. It's just
well, it's certainly not obvious. You have to actually take general relativity and understand how you derive this number. So I'm just stating the result without deriving it. But if you, for example, have a crazy universe, which is very small and then keeps expanding at some velocity, and then it gets to the point where it's where it's exactly 8 times smaller than today, and then it stops expanding. It just sits there. Then you have a galaxy and it's emitting some light to us, and then after the light was emitted, you say, oh, okay, I'm going to start expanding again. And the universe starts expanding again, and then when it's the present day size, you decide, actually, I'm going to stop the expansion. The universe is now, again, not expanding. So then there's no relative velocity, either at the time the photon was emitted or at the present time when we receive the photon. The universe is stationary. There's no velocity, but you would still see a factor of 8 times longer wavelength, because this has nothing to do with the expansion rate. It only has to do with the fact that the universe expanded by a certain factor.
Yeah, I think you could also see this from the balloon, right? It does not matter how fast the balloon expanded, rather just how big it ended up.
Yes. One way to intuitively think about this is the density of the universe is changing and the background potential is changing. And it doesn't matter, the velocity doesn't matter. This, I should say, is a very common confusion. So I'm glad you asked, because even if I ask the graduate students here, 9 out of 10 thinks that this cosmological redshift has to do with velocity. And it's like a Doppler shift, but it's actually not. So yeah, that's an interesting fact. But so now we can return to the discovery that there are these quasars. We know they are there. They look exactly like the closer objects, except they're so far away that the universe was 8 times smaller when they were produced. Now, again, let me ask the same question. Is 8 times smaller universe, is that a very early universe, or is it? This is an open question. Do you think of that as a very early time in the history of the universe, or if you convert it into time, what do you think was the age of the universe at that point? Again, not a trick question, and you can just throw a guess. If you have some explanation, you can tell me. Or you can just guess. Okay, no guesses.
I'm going to guess about 1/3 of the age.
Yeah, so that's not a bad guess. So the age and this, if you think about it, well, we know the universe is. Well, actually, we didn't say that, but you know, the universe throughout most of its time was decelerating. So in fact, this expansion factor as a function of time is not linear. It's decelerating. So you can convince yourself that 1/8 the size corresponds to something similar in age, but actually a little higher, not a little lower. So you guessed 1/3 instead of 1/8. Is more like 1/20th. The age of the universe is 1/20th, or something, 5% of the present age. So that's an important distinction because it's actually quite early. It's quite early on in the evolution of the universe. So the current age is 13.7 gigayears. So these quasars, which we see, they lived when the universe was about. Actually, the record holder is lived when the universe was about 700 million years old. So 5% of the current age.
Zoltan?
Yeah.
A quick question. Could you set the scene a bit about like the history of the universe? Because I mean, I think this is, of course, it's all relative. But so the universe is reionized and stuff, and the galaxies. Could you just sort of give us a feeling of where we are in the history of things?
Yeah, no, that's actually an important part of this story. So far, all I said was that we live in a universe that's 14 billion years old, and we see these quasars when the universe was 700 million. And is that interesting? Is the question. Why is that interesting? And so the way I would like to answer your question is to say, well, when do we expect the first objects in the universe to appear? And what else have we seen at such large distances? I suppose these are two ways to answer your question. So first of all, we have seen about 200 of these quasars, roughly speaking. So it's a decent sample of data. We have about 200 quasars at these very distant early epochs. And there are a comparable number of galaxies which were detected around the same time. and they actually look, these quasars, they look very similar to the quasars that we see in the more nearby evolved universe, in the sense that they have the same brightness, they have the same kind of spectra, they have the same ratios of lines, implying that the composition, the chemical composition of the material doing the emission is basically the same. So that's very interesting, because we know the masses of these black holes. Actually, I didn't explain. So you should, you could ask me this, but you could ask me how, actually. But we know the masses of the black holes that power these quasars just based on their luminosity, because they're so bright. I think I should explain this, that because they're so bright, we know the black holes that are powering them must be very massive. Well, maybe, let me think. So maybe I'll skip this. Somebody, well, no, I think I will explain. There's something called the Eddington Limit. Can you please raise your hand or tell me if you ever heard the Eddington Limit?
Raise your hand, it's going to be difficult, but Mark or Jose El Stereo would like to speak.
No, I don't.
We were
I don't
raising
know
our
what that is.
hands. We were raising our hands.
So can you give us or can you explain what is this Eddington Limit?
Yeah, so the Eddington Limit is important, because if you have a black hole of mass m, then very roughly at least there's a maximum luminosity that can be emitted by this quasar. And at least the explanation for why, so it cannot be arbitrarily bright. And the reason for this is actually quite simple conceptually, because if you go back, well, because if you want to produce luminosity, you have to feed the black hole at a certain rate. So if you want to, so as we discussed actually previously, the luminosity of the quasar is generated by liberating the gravitational potential energy in this inspiraling accretion disk. So there's an accretion rate. Material has to flow in at a particular rate. And that produces this luminosity. This luminosity is sending out photons, and the photons can collide with the infalling electrons. Now, do you know what happens when a photon collides with an electron? This is not just astrophysics. I think this is general. You might have encountered this in your other classes.
It can scatter.
Right. So it will scatter on the electrons, and in the process of scattering, what happens to the momentum of the electron?
Well, the electron momentums changes depending on the type of scattering. Maybe elastic scattering, inelastic scattering. I don't know.
Yeah. Where
quantum scattering, for example, or
yeah, very good. So in the simplest limit, which I don't think we need to go into, but in the limit that is relevant here, it's simply you transfer the photon's momentum to the electron, and all the photons are coming radially from a point source. So if you're coming out, the photons are all emanating from a very small region, coming outward, impinging on electrons, and transferring their momentum to the electrons, which is, if you have a certain momentum per unit time given to the electrons, it's equivalent to an outward force. It's a radiation pressure. So effectively, there's a force pushing the electrons outward. That's called radiation pressure force. And this is just scales linearly with the luminosity of the central object, because if you have 10 times more higher accretion rate and you generate 10 times higher luminosity, this outward force will be 10 times higher. Does that make sense?
Yes.
So then, good. So then, that means if you try to make the object really bright, eventually, this radiation pressure force would be larger than the inward gravitational force, and it would shut down the accretion, which is powering the luminosity to begin with. So therefore, the rough thinking is that it's impossible to produce for a long period of time in a steady state fashion a luminosity that's brighter than this so-called Eddington limit. And these quasars are basically so bright that even if you assume that the black holes are powering them, are the maximum, they're producing the maximum luminosity, this so-called Eddington luminosity, even then they have to be 10 to the 9, and in fact the record holder is 10 to the 10 solar masses. So that's basically the exciting observational puzzle. We have about 200 black holes when the universe was only several hundred million years old, and their masses are 10 to the 9, 10 to the 10 solar masses. Now, why is that surprising? Because you asked about the history of the universe, and if you only have 700 million years, it's already short, relatively, but in fact, when Pau stopped me, I was about to explain that we think we understand how the original perturbations produced at the beginning of the universe grew and collapsed on themselves. And so we know that this happens when the size of the universe was roughly 20, 30 times the present, smaller than the present day size. So maybe when the universe was 200-300 million years old. And before then, there were no galaxies, or in fact, there was no astrophysical objects as far as we know from our theories. This is theoretical with some constraints from data, but essentially we don't expect any object to be in the universe until 200-300 million years after the so-called Big Bang. And then we expect the first stars and mini galaxies to appear, and in principle there you can have stars forming. And now I'm going to my punchline here of this. Why is this 10 to the 9, 10 to the 10 solar mass black hole so puzzling? And the point is basically that there's very little time to grow such a big black hole in the, let's say, 300-400 million years between when we expect the first anything in the universe to appear and when these quasars are observed. Time is very short. And now I should just say more generally, if I ask you, how do you, well, maybe this is too challenging. Well, let me ask a good question. So I think several times probably you heard about the LIGO results, for example. So I think Chian alluded to the discovery of stellar mass black holes by LIGO. So we know very well that stars leave behind black holes when they exhaust their fuel. But do you remember the largest masses of black holes that can be produced by the remnant of a star? Does anybody remember or know a number?
The largest mass left by the remnant. What do you mean?
So we know the universe can produce black holes, but the way we know for sure the universe can produce black holes is stars are formed in galaxies. The stars shine by nuclear fusion. We established this a while ago. But then nuclear fusion eventually has to stop because you exhaust all the nuclear fuel. And after that point, stars which were originally massive, they cannot avoid collapsing to a black hole because nothing can hold. So therefore we know the universe can make black holes. But since we're trying to explain very big black holes, I'm asking if anybody knows what is the largest black hole that can be left behind by a dead star.
Yes, so the question is if we observe, as we do, or we think that we observe black holes with masses of beyond 10 to the 10 solar masses, how can you produce that, right? So if a massive star collapses, what do you think is the largest mass that a black hole could have out of that collapse, right? It goes in that direction.
Yeah. I want to...
So what do you think, people? Mark, Klinger, Jose.
Sir.
Yeah, go ahead.
No, I just wanted to ask, are you trying to hint towards the stellar mass black holes of like 30 and 40 solar masses that LIGO had seen? Is that's where
No. What Sultan is trying to say is that if Joseph in the universe... Sorry, Sultan, I'm intruding your...
Yeah, please, go ahead.
If you observe at the center of our galaxy a black hole with a mass of 4 million solar masses, and we have hints that supermassive dark objects exist with masses larger than 10,000 million solar masses. So how can you produce that? If you think of the collapse of a star, what is the largest mass that you could have in that collapse? Compact remnant. 10,000 million solar masses? I don't think so.
Yeah, maybe. Well, let's simplify the question. What is the most massive star you ever heard of?
I know the answer. People, come on, talk. Mark Klinger, Yorgo Vretinaris, somebody, Veronica.
Let me ask differently. Have you heard of a 100 solar mass star or as large as 100 solar masses? Maybe people just don't actually know the answer, but you could guess.
I think
it's funny if you're wrong, but you have to play along.
I think few hundreds of solar masses is something I think I cannot put a number, but I guess 100 to 1,000 solar masses should.
Yeah, very good. So I think that's actually about the right answer, just observationally. I'm sure you heard our sun is a typical star. It's 1 solar mass. But in our galaxy, there's a range of stars, and we believe the largest one that we've actually seen is a few hundred solar masses. And the reason I made you guess this, because that's a problem, because we have a few hundred solar mass star, when it dies, at most will leave behind a few hundred solar mass black hole. So now we have to explain how do you end up with black holes which are a million times more massive. So now I want you to guess, how would you do that?
Mergers? If multiple solar mass multiple of these massive black holes are merging, that can be one scenario.
Yeah, very good. That's one. Now I want people to just come up with ideas. So just again, think out loud.
Yes.
And actually I can give away the answer, which is nobody knows. But so the rest of this talk would be pure theoretical possibilities, because nobody knows the answer. Therefore, you can guess, and you will not be wrong. So mergers is clearly a let's say an obvious idea. We know for sure stars exist. We know they leave behind 100 solar mass black holes. In fact, we know empirically because we have seen them with LIGO. So,
we could also think about shifting the problem to the primordial.
That's a very good idea also. So maybe something in the early universe at the time of the Big Bang was producing giant black holes. What about other ideas? Is there? It's not a trick question. Just how would you do it?
Yes, Cuba people. Yes, sorry. Go.
A very big gas, a cloud of gas that directly collapsed.
Yes, very good. So.
Sultan, you're muted for some reason.
Oh, I don't know what happened.
Yeah.
So yeah, very good also. So a third suggestion is you have some gas cloud, which is very massive, 10 to the 9, 10 to the 10 solar masses. For some reason, it collapses directly to a black hole. What about other ideas? I want to hear.
I don't know. I'm just taking a long shot. Something to do with perturbations. I don't know.
Perturbations of what? Long shots are good. You can.
I don't know. I mean, I just gathered that from the points you made before. So I'm sorry. I don't know.
No, but what are you imagining is perturbed?
Of space-time.
Oh, I see.
And so, I mean, because of GR, then it would then matter too, right? Would get condensed into it.
So then that sounds like a chicken or egg problem, because what is it that perturbed the space-time?
Yeah, exactly.
It would already have to be an extremely compact and dense object. Now, what I want to let's hear one more idea before I say a few things.
Yeah, maybe a contribution from Cuba. Come on, Jose.
Here's
I have a question.
Yeah.
Excuse me. It is about something you talked about earlier. When you say that the universe expands, what do you mean? The space-time expands itself? If it does, where to? Where the universe expands into?
Okay, that's a good question also. That's one of the 3 questions I can never answer.
Okay, thank you.
Because, and
is there any?
The best answer I can give to this question is it's not expanding into anything. And yes, space-time itself is expanding. And if you imagine that the universe, instead of 3 + 1 dimensions, was 2 + 1 dimensional, so 1 less dimensions. And you imagine that the universe is the surface of a balloon, then it doesn't have a boundary, and the balloon can expand to twice its size without expanding into anything. Because the balloon, we are strictly saying that the universe is the surface of the balloon. It's not the inside of the outside of the balloon doesn't exist. It's not part of the universe. Only the surface of the balloon. So you inflate the balloon and it just everything becomes twice as large, but it's not expanding into anything. There's no boundary.
Yes, but the balloon is expanding in, I don't know, the air of the room where you are. I don't know. That's how I see it.
That's right, but this is why it's hard to process mentally. But what I'm saying is, suppose in the balloon analogy, there's no air, there's nothing outside the balloon. That's just an analogy where we say if the universe was two-dimensional, then you can think of it as the surface of a balloon. But in that analogy, there's nothing outside of the balloon and inside. That's in 3 dimensions. It doesn't exist. We're saying it does not exist. There's nothing outside or inside. So there's no air into which it.
But we still need an extra dimension to think in the expansion of the universe, I guess.
Well, if you want to visualize it from your human, 3-dimensional human perspective, but you don't actually need it's not necessary. Doesn't enter any equations and any phenomena. So if you want, you can make the analogy the other ways. If you had some hypothetical being where instead of 4 + 1 dimension, it's 5 + 1, and you can imagine our 4-dimensional space-time is expanding into some kind of 4th spatial dimension, but it's unnecessary. Maybe it would make the 5-dimensional humans happier, but it doesn't involve any observation or any equation.
Sorry, if you have a background
Thank you for the answer.
Yeah, so to the person who asked the question, maybe a different approach. If you have a mathematics background, maybe it's the same problem as the sphere. If you try to imagine the 2-sphere, so just the surface of a sphere, what you will do is you will imagine it embedded in 3-dimensional space. So you will think of that object not as the object itself, but rather it's embedding in a space that's 1 dimension higher. But really, the sphere itself does not need to be embedded in a space to exist, and that's kind of at the heart of defining what a manifold is. We know by some theorems that we can always embed a manifold in some, Rn, but it is not necessary. They can be defined completely independently of this. And so I guess our universe would be the manifold, which does not need to be embedded in a higher dimensional space to exhibit this expanding. But if we want to think about it, we would have to think about it in a +1 dimension.
Yeah. So let's go back to black hole. So any other ideas?
Can somehow the primordial black holes be also extended big sizes?
Yeah. So let me summarize. We heard one option was merge together many stellar mass remnant black holes. Another option was sometime at the Big Bang, some process produced very massive black holes. And then a third option was a giant gas cloud, which is much more conventional than the early universe. Just some gas cloud somehow, for some reason, collapses directly to a black hole. And then a fourth was some perturbation caused space-time to be dented. And I would say that's maybe lumped together with this primordial idea that something weird happened in the early universe. I do want to say that somebody should say the obvious other option.
Okay, I'll say it then. Because is growth through accretion ruled out or not?
Yeah, very good. So, I mean, I'm glad somebody thought of that. So we've been saying all along that black holes are shining very bright because they're accreting, because a disk of material around them is falling into the black hole. And that of course can in principle cause the black hole to grow in mass. So that's another option. You simply start with a small black hole, which we know how to produce from a stellar remnant, and then if there's a gas plasma around that black hole, it can grow it.
I have one question to go with that. What is the e-folding time that we would use to work out if that's plausible?
Yeah, so very good. So now the puzzle comes. So I would say these ideas were all good. Thanks for suggesting these ideas. I would rank these as the the least controversial, most obvious ideas would be grow it by accretion or merge a lot of already known black holes. And so those are the ones to consider first. Now, if you consider and it turns out that all of these ideas run into difficulties, which is why this problem is so interesting. So let's take the first example of the accretion. What is the problem with that idea? It's exactly as you say, the e-folding timescale is too long. And the explanation for this is also actually quite simple. I've explained to you that there's this thing called the Eddington luminosity. And if you think about it for a second, so go back to my explanation of the Eddington limit. I said that if you produce certain luminosity, you exceed the radiation pressure force pointing outward is exceeding the gravitational force pointing inward, right? This is what I said. You agree? So if you write an equation, what would this look like? On the left-hand side would be the radiation pressure force, which is proportional to the luminosity, times some cross-section for the electron scattering, times some constants. The other side of the equation, the gravitational force, would just look like Gm over r squared. So this means this Eddington limit is proportional. So, okay, somebody should tell me. So what do you think is the scaling between black hole mass and this Eddington luminosity? I gave away the answer practically, but if you paid attention, you should be able to tell me. Suppose I have a 10 times bigger black hole. Increase the black hole mass by a factor of 10. How much could its luminosity increase based on this Eddington limit?
By 10?
Yeah, exactly. So it's linear. Just because you're equating some radiation pressure force, which is proportional to L, the luminosity, you're equating it to the gravitational force, which is proportional to M. So this means the maximum luminosity is proportional to the mass. Now the luminosity, this is a bit maybe less obvious, but the luminosity should also be proportional to the accretion rate, m dot. So you're growing the black hole at some rate by throwing gas at the black hole at some rate, m dot, dm dt. Now, this dm dt is the rate at which you're feeding the black hole. Some fraction of this will grow the black hole, and some fraction of it will come out as photons ultimately. So that means there's some constant which is essentially a few percent of the mass that's falling to the black hole, which is coming out as photons. So the luminosity is also proportional to m dot. So now we have two equations. L is proportional to m if you maximize the luminosity, and L is also proportional to m dot. Basically, if you're feeding the black hole 10 times more rapidly, you will try to be 10 times more luminous. I think that's kind of makes sense. So this means m, since both m and m dot are proportional to the luminosity, that means m is proportional to m dot. So that means that's a simple equation. That means m is growing exponentially. And now if you plug in the numerical constants, which involve g, the Newton's constant, and the electron scattering cross-section and the speed of light, if you plug these in, you find that the exponential timescale for this growth is about 50 million years. And now you can take out your calculator, and I told you that there's maybe 300 million years if you form some stars as early as we think are possible in models for how perturbations in the universe collapse into anything. So you have 300 million years, and the exponential timescale is 50 million years. So you have roughly 6 e-foldings available. So e to the 6 is about 400. So that means if you grow at the maximum allowed rate at all the time, from the birth of the first star, which left behind a 100 solar mass black hole, you can only grow by a factor of, let's say, in this example, roughly 400. So this is a problem. You somehow, so the maximum growth in this simple picture doesn't actually allow you to grow a single stellar mass black hole to the massive ones that have been observed. So that's the main problem with this accretion idea. The merger, let me go to the next one, the mergers. So just to illustrate here that also has a problem. Now you're trying to take, so I don't know who suggested this, but it was a good idea that we know we have 100 solar mass black holes left behind by early stars. If you can merge together 10 to the 7 of these, then we can end up with our big black hole at the end. Now the problem with this idea is very different. It's basically that I don't know if this came up in any previous talk, but first of all, this means black holes must be able to merge. So 200 solar mass black holes roughly must be able to merge together and give you a 200 solar mass black hole, and this process has to repeat many, many times. So here's the problem. When two black holes merge, and this is a very interesting result that has been obtained rigorously only about 10 years ago in general relativity. When you take two black holes, put them close together, it is possible for them to merge because they start orbiting one another. They emit gravitation waves, as nicely explained by Qian in previous talk. These gravitation waves, I think everybody is probably familiar with the idea that they carry energy. And the orbit therefore shrinks. And ultimately the two black holes must merge because their orbit keeps shrinking. And the energy is going into gravitation waves. Now, what's less commonly explained is that the gravitation waves, which are emitted in during the orbital acceleration of the binary, also carry momentum. Now, maybe that's something I can also ask you. Why do you think? Are you surprised that? Why would these waves carry energy and momentum? Does anybody have a intuition or explanation?
Silence, people.
Maybe it's getting a bit late, and maybe this is too tricky question.
It is.
But it's a notoriously difficult question, right? Which took a while to settle.
Yeah, but there is a very basic point I wanted to point out. If you imagine two black holes like this, and they're going on a circle, you've probably seen pictures of the gravitation waves, even in a cartoon sense, but they cannot be circular. They have to have some kind of spiral pattern because there's 2 point masses and the waves emanate from the 2 point masses. So I think you will believe me if I say this cannot be concentric waves if you're close to the binary. Right? Do you agree? You have to agree because the system is not circularly symmetric. So these waves actually are spiral shaped, and they have a preferred direction at any given moment, and therefore they have a net momentum. And this causes the black holes, when they merge, to conserve momentum and recoil. So once the merger happens, the black hole remnant, which is indeed a single black hole resulting from coalescence of previous black holes, experiences a recoil. And that's the problem, is that as a result of this recoil, the black holes tend to fly out of the early galaxies. So that's a major problem with trying to merge 10 million of these objects, because every time you do you have a merger, you have a chance, a large probability that you lose the merger remnant, because you will recoil and fly out of the galaxy. So that's the main problem with this second idea. So I think it's getting a bit. Yeah, go ahead. Go ahead.
Sorry, I just wanted to say that you are saying, but then that also makes, so this recoil will then definitely make observing the mergers of supermassive black holes difficult as well, right? Because you're saying if they recoil, then they have left their host galaxies. So then, but I just don't, I can't visualize maybe very well when they recoil, then when they're plunged out of their host galaxies, and where do they go? Like they're still part of maybe some cluster or something. So I just don't understand why in future they can not merge with something else, or they can also accrete simultaneously wherever they travel to. I don't know, maybe I'm not framing my question very well, sorry. No. Sorry. Yeah.
I think you're muted again.
Can you hear me now?
Yes.
Yes.
Yeah, I don't know why I didn't touch it, but I get muted somehow. So I think you asked two questions. Basically, what happens during this recoil to the remnant, and does it leave the galaxy, or does it leave the surrounding cluster of the galaxy? And second question was, why does that actually prohibit a sequence of mergers? So
yes.
the answer to the first question is, I think you're thinking of it exactly right. You have two black holes in the middle of the galaxy. They spiral in the supermassive when they're already supermassive, let's say, or almost supermassive, and they coalesce. And that almost instantly, this recoil velocity is imparted. The time scale on which you impart this recoil is really, really short. It corresponds to just one last orbit of this binary before they plunge and merge, which is basically a time scale of a minute. So after maybe 100 million year process of merger, it takes only a minute to accelerate to a speed which will unbind the remnant and will actually fly out on a linear trajectory pretty much from the nucleus of the galaxy. And this kick, the magnitude of this kick and its direction depends only on a few parameters, but it depends on the black hole masses, M1, M2, the spins of the black holes, which are vectors. So spin 1 and spin 2, and those are vectors. And it can be, the kick can be between 0 and several thousand kilometers per second. So it's a statistical distribution if the black holes are coming in mergers on random orientations and random spins. But in a large fraction of the cases, you impart velocities which are larger than the escape velocity from the galaxy, so you just fly out. Some few cases, it's possible that the kick will be small and the black hole remnant remains in the nucleus. Now, I should say that
I have a question.
Yeah.
Guys. So
yeah.
actually, if I think about the interaction rate, if we say we want a high interaction rate of black holes, then it wouldn't it be? I mean, it scales as the density and the speed. So if we increase the speed, and we can also increase the density, wouldn't like if we would just increase the density of black holes or black hole merger to an incredibly high, maybe unphysical value, it would be even helpful if they are gaining speed, right? So we would increase the merging rate even more.
That's right. So as long as they remain bound. So in fact, what you're saying is one possibility that people are studying at the moment, that there's a very dense cluster of these stellar remnant black holes, so that the escape velocity is higher. I can just tell you the bottom line is it's hard to arrange, fine-tune such that the black holes after mergers they remain bound and merge enough times. And remember, you have to actually do this 10 million times. I mean, you have to build up to 10 to the 9, 10 to the 10 solar masses. So that's very hard.
Yeah, that would be like the optical thick case. Yeah.
People are looking for cases where you can resolve the position of the quasar because it's relatively nearby quasar and you can actually resolve the galaxy. And there are a few examples of observations where the black hole is not in the nucleus, but it's offset. And those are very interesting, but people cannot really prove that that's a result of this recoil.
Okay.
But otherwise, so there's another unresolved issue of how you can actually see such a quasar that's flying out of the galaxy. How do you prove it was a result of a recoil? And then your second question was, well, why is this bad for mergers? And the answer to that is just that in order to merge, you need to encounter another black hole. So if your black hole has been ejected from the galaxy and is just flying through intergalactic space, or even if it's in the intercluster medium, the likelihood that it merges, that it enters another galaxy, and there it sinks to the center and merges with another black hole is just very small.
No, I had the similar picture as Mark was pointing out that it's in a dense environment. So somehow that's how I was thinking that even if it flies away, why can it not accrete the neighboring matter if it's flying out in a denser environment? So and then put on mass. So I was thinking maybe of a very complicated scenario in my head.
So I think now you said the word accretion. So I think you're going back to the idea of some kind of combination.
Yes, I was thinking the same, that it should be some combination because there's no hard and fast rule that it has to be only via one process. So I was just thinking.
That's a very good thought. Again, we don't know the answer, and I think that's a very likely scenario where you combine these two things. You both merge and accrete. I think it's getting a bit late for me, but I have to wrap up at 2:30, so we have about 9 minutes, which I don't think I will answer these puzzles, but I could answer more questions, or I could say couple more things where this puzzle is headed in the future.
Maybe that's a good idea, right? So it's not you solving questions or explaining the whole thing, but actually motivating this field, or trying to show the students what is to be done yet on this matter.
Yeah. So I think you're asking really good questions, and you're already getting into where one kind of so there's been a lot of modeling of dense clusters and how many mergers you can expect, and this combination of accretion and mergers is actually a very good direction. It has not been fully explored. The other direction which we haven't mentioned is there is in principle, which I think is more related to the other suggestion, that there is a gas cloud which can directly collapse to a black hole. And is that possible? And another way of saying that is that you somehow have to evade this Eddington limit. Because if you're collapsing a large cloud very rapidly, you tend to generate a lot of radiation. And there is a possibility, and more research is needed there, of maybe this Eddington limit can be avoided. And the way it can be avoided is that the gas cloud is so opaque that the photons that are generated in the central region, because of the collapse or because of a black hole already in a small black hole in the center, is accreting and producing luminosity. They have a luminous core in this cloud, but the photons never propagate outward because the gas is so optically thick that the electron scattering. So the interesting possibility is that as I mentioned, this Eddington limit comes from photons emitted in the central region, and the photons are moving outwards and impinging on electrons. And in the optically thick limit, where there are many electrons, you can think of this as a random walk problem. So it's a mathematical problem of a random walk. The photon is coming from the middle and is trying to random walk. And as you may remember, the property of random walk.
You're muted again.
You're muted again.
That's funny. I'm not touching anything and I get muted somehow. So the random walk essentially slows down the photons. They're moving outward from an optically thick medium much slower than the speed of light. By the effective speed of photons moving outward in a cloud whose optical depth is tau. Usually the symbol tau is the optical depth, is c over tau. So it's the speed of light divided by the optical depth. So if the optical depth is very large, you can end up in a situation where the photons are trying to move out at a speed which is slower than the infall speed of the gas. And that's a very promising way of avoiding this radiative feedback and suppression, because the photons are essentially trapped in the inflowing gas and just also swallowed by the black hole without doing anything. So this scenario is realized only if the accretion rate is very high and the cloud is very dense. But essentially the black hole is then eating not just the gas, but also eating the radiation. And that's another research direction, because you have to model the propagation of the photons, and it's probably not spherically symmetric, so you have to worry about photons breaking out in polar direction, where the accretion is in a disk situation. So these are harder problems.
I have a question on this. Would there be fusion starting at some point?
So generally, in an
I was
equation,
just comparing it to a star, basically.
no, yeah, it's very good. Actually, very, very nice question. So it depends. I think nobody knows, but I think it depends on the angular momentum of the gas. So when you actually solve the equations for these models, and you have the model of the accretion disk, the key is the temperature, because fusion requires temperatures which are above the nuclear energy, so 10 to the 9 Kelvin. So you have to reach very high temperatures, 10 to the, of order 1 billion Kelvin. And in the accretion disk, you don't reach these temperatures. So the general thinking is there's no nuclear fusion taking place if the accretion is disk-like. Now, in a star, as you just said, yes, there you compress the center much more by the weight of the spherical atmosphere, and it gets very hot, and you have fusion. And another variant of this idea is that what we so far just casually said, the spherical cloud collapses directly to a black hole and eats its own radiation, is actually going through a stage which is more fairly characterized as a supermassive star. And actually, if you ask me personally, Zoltan, this is my favorite idea because it's actually quite natural. Maybe I'll just explain this part because I think this is really, really attractive to me. So it turns out, in this case, there would be nuclear fusion because you basically first form a star. You have a big, very dense cloud, which is collapsing very rapidly. And it's basically first producing it turns on effectively a star. It starts nuclear fusion in the center. But it's very different from a normal massive star. And there's only one key difference. But I would have to explain most of stellar evolution. So let me ask you one question. Why do you think there are no stars massive than, as we said earlier, a few hundred solar masses? Why don't we have a 4,000 solar mass star in the Milky Way galaxy? Any guesses? What limits the masses of stars on the massive end?
I know, but I'm not going to say it.
Again,
People.
you can get, well, just think of anything you think might limit the masses.
Gravity cannot hold it together.
So no, it's not just gravity.
If it's a star and it's not gravity, what is it?
So I'm going to give you just a 30-second explanation. So the reason we have a maximum mass of stars in our galaxy is that stars form in a similar process. There's some cold cloud called a molecular cloud, and it's due to its own gravity, it's collapsing and it's becoming dense and turns on nuclear fusion. And this star is radiating, and there's something called Kelvin-Helmholtz contraction. This just means that you have an opaque blob of it's called a protostar because it's a stage of a star when it's about to form, so out of a collapsing cloud. And it forms something called a protostar, and it's opaque, and on the surface it's emitting blackbody radiation, thermal radiation, and it's contracting and squeezing the center and turning on nuclear fusion. And the star becomes very small, very compact, because it's contracting on this time scale on which it can radiate away its thermal energy, called the Kelvin-Helmholtz time scale. So this ball contains thermal energy, its temperature has to go away, it has to be deflated so that it can contract. And that time scale is 100,000 years or something like that, a million years. So during that time, the star collapses and becomes very small. And it becomes, the surface area of the star is very small. And therefore, its spectrum, this may be a little advanced and we'll have to talk more about this. But because it's very small, its spectrum shifts to high photon energies. If you ever taken any class, then you know that the total radiation is black body emission is sigma t to the fourth times the surface area. And if and this is the luminosity. So luminosity is equal to sigma t to the fourth times the surface area of the protostar. And if the surface area is very small, then sigma t to the fourth has to be large. So the temperature has to be large. So the photons are very energetic, and when they come out, they ionize the hydrogen, helium that's falling in, and prevent further accretion. So that's it. The reason we have a limit on the masses of stars is that star starts to contract, and then they're growing, but when they grow to about 100 or 200 solar masses, they emit too much radiation, and it's ionizing radiation, and it shuts down the accretion. You cannot grow further. Now, in the early universe, this can be different because the galaxies are much hotter and much denser, and the accretion rate is much faster, and the protostar is doing something similar. So whoever suggested this direct collapse of a cloud, this is essentially an elaboration on this. You have a very dense cloud, trying to form a star, just like in our galaxy. The major difference is that the accretion rate is much higher. So during the time this protostar would contract, it's already accreted more stuff on the envelope. So never able to compress to a small star. So it becomes very bloated. And the surface area is very large. So sigma t to the fourth times the surface area is now the luminosity, but the surface area is very large, and the temperature therefore is smaller. So these stars don't emit, these supermassive stars don't emit ionizing radiation. And so they never shut themselves off until they grow to about 1 million solar masses. And at that point, a completely different piece of physics, a general relativistic instability, causes them to collapse to a black hole. This is basically the scenario where
you're muted again.
Yeah. So in this scenario, it's possible to form a 1 million solar mass black hole, which is arguably first a supermassive star, and it happens in 1 million years. And again, this is a subject of active research, not a final answer.
Fortunately.
Yeah.
So it's been a long discussion and a lot of questions from Zoltan and from the audience.
I'm happy to answer emails.
Yes, because you mentioned that you have to go, Zoltan. I have Zoltan's email, and of course you can find him on the internet. And again, I would encourage that you write to him. He's a very nice guy. I know him personally, and he does not bite. And so,
and
I don't know.
Yeah, I'm happy to answer questions by email.
So unless you have, yes, who's that? Somebody wanted to talk, I think, I don't know. Okay. Unless you have some comment or whatever, let's resume tomorrow. Tomorrow we'll have